record. So today's a pleasure to have with us Josephine Suh from the Kavli Institute at UCSB in California. She will talk about gravity from probability. Thank you.
Thank you for inviting me to give this seminar. So I'll be talking about some work, some results that I've obtained recently that I'm quite excited about. And towards the end, I'll briefly, hopefully, also discuss where I go, where I see things going from here, what my future plans are. So, so the premise of my research, and a lot of the research in my field for the past 25 years or so, has been a certain duality between gravitational and quantum systems. And this is called the anti-de Sitter space conformal field theory correspondence, or more generally holographic duality. And the main idea is that basically you can have a many-body quantum system in some strongly correlated phase, which has as its dual description gravitational theory in one more spatial dimension and negatively curved space-time. So naively, the quantum theory doesn't have anything to do with gravity. So the fact that it has some alternative representation of its dynamics, that is a gravitational theory, has been suggesting that there are some connections waiting to be found between gravity and quantum theory. So an important idea or important hint as to what those connections could be came about a decade later. And this is called the Ryutakenagi Formula. So the formula, the Rutakanagi Formula, is an equality between an area, between the area of a surface in the gravitational theory and the quantum or von Neumann entropy of some density matrix in the boundary quantum theory. To be more specific, suppose we chose some spatial region R in the boundary theory. There is some density matrix rho R associated with that region, because we can start with the density matrix for the entire system and trace out the spatial area that's not R. And strangely enough, the gravitational theory seems to be such that a surface which is anchored at the boundary of R and which has area that is extremal compared to neighboring surfaces, the area of that surface computes the von Neumann entropy of rho R. And so the lesson to take away from this was that somehow the geometry or the bending of space-time in the dual gravity theory is capturing the information content of the boundary quantum theory in some very direct manner. A third and more recent inspiration for the work that I'll present comes from the fact that it has been shown that characterization of dynamics in a quantum system is important in connecting it to gravity. So for example, an analysis of certain correlators in the quantum theory, which capture the notion of chaos or trajectories in phase space that diverge exponentially in time. It was this analysis that led to the discovery of a 0+1D quantum system that has a gravity dual. And this is called the SYK model. So the SYK model is a 0+1D quantum system with an n number of Majorana fermions, which have all-to-all interactions in the Hamiltonian. And here I'm showing that in one term in the Hamiltonian, you have a q number of fermions that are coupled with some coupling J. And in 2018, Kataev and I showed that the low energy theory of this SYK model can actually be quantized and solved exactly as a theory of particles, of certain particles on ADS2. The low energy theory also has a very simple gravity dual with very succinct classical equations. And so I began to think that this is the simplest possible instance of holographic duality that we could have, where we have complete knowledge and control over the quantum theory. So at least in this instance, we should be able to derive the gravity dual directly from the quantum theory. So the question I was asking was, can we deconstruct gravity in this example? Meaning, can we take apart the gravity dual and sort of formulate it in relation to the quantum theory from scratch? So the kind of questions I was asking were what kind of observables or expectation values in the quantum theory are relevant? And what aspects of the particle theory are Einstein's equations expressing? So I'm happy to report that I succeeded in answering these questions, and I'll be reporting on them in a forthcoming paper. So to succeed, we have to use notions such as probability space, stochastic process, a Markov process, which is a type of stochastic process and its generator. And a brief summary of my results would be that by analyzing certain expectation values in the quantum theory, we show that the dynamics of the quantum system induces a Markov process in the measure space of an observable. And then we show Einstein's equations are in fact solving for a stationary probability distribution of the Markov process. And this suggests a new program going forward, which is that to reformulate gravity and discover its full relations with quantum mechanics, we can build bridges to stochastic processes and probability theory, starting from quantum theory. So the outline for the rest of my talk is, first I'll summarize the duality I'll be analyzing, which is between a theory of particles on ADS2 and a simple gravity theory called JT gravity. And then I'll introduce some basic notions from stochastic processes that I'll be using. The next step is actually to adapt some of those notions to a quantum system, because in the end, we have a quantum system that we want to analyze. And finally, I'll describe a Markov process in JT gravity, of which an important component is actually joint probabilities, which we extract from certain expectation values. And then using this Markov process, I'll derive Einstein's equations and state an inequality between area in the gravitational theory and stationary probability from the particle point of view. So that's the outline. Are there any questions at this point?
Unless you're going to address it later, how does a tensor field emerge in that consideration?
Yeah, so because this is a simple theory of gravity, sort of the thing that Einstein's equations will be solving for will be a scalar field. And so that's why we're able to equate it with probability. But more generally, I think it will be clear from what I present that there may be ways to generalize that to cases where you actually have more degrees of freedom in the gravity theory. So hopefully, yeah.
So I had a question. You said that solving Einstein's equations gives you a stationary probability distribution or something. How do you interpret the solution to Einstein's equations as a distribution? If you're going to answer this later, that would be fine. But.
Yeah, because so Einstein's equations are solved on a rigid two-dimensional spacetime, and it's actually solving for the area of compactified space at a point. So you actually have a distribution, if you like, over the rigid two-dimensional spacetime, which itself can be thought of as the target space for some observable. So yeah, this will be part of my explanation going forward. Okay.
I have a more mechanical question. So you showed you have n Majorana fermions, and you wrote this Hamiltonian, which had these fermion to the Q insertions of fermions. So Q is less than n, I suppose, but does it matter how big Q is, or that's a free parameter?
Yeah, Q is supposed to be order 1, like it can be 4 or 6 or 8 and so on. Okay, but Q is fixed. In the limit of very large Q, you get, actually, I suppose you can consider, so an asymptotic limit where Q is of order n or even larger, and those have different, physics. But the kind of physics that I'm describing applies when you have an order 1 number, where Q is order 1. Okay, so duality between particles on ADS2 and JT gravity. So JT gravity is a simple theory of gravity where space-time factorizes into some portion of rigid ADS2 and a dynamical sphere at each point. And by sphere, I really mean compactified space. So if you look at the action, it involves a 2D metric and a scalar field called the dilaton, which actually represents the area of the sphere at each point. And so there's a bulk term in the action, in which the dilaton appears linearly. So this constrains the curvature of 2D spacetime to be constant or rigid. So we have a rigid 2D spacetime. But then if you vary this bulk action with respect to the 2D metric, you actually get Einstein's equations, which are solving for the dilaton. So this is the setup. And there's also a boundary term in the action, which involves the curvature of the boundary of 2D spacetime. Now, because this bulk action actually vanishes exactly due to the dilaton appearing linearly and acting as a Lagrange multiplier, we can in fact view JT gravity as a theory of the boundary of 2D spacetime only. And it turns out, as we worked out in these papers, it turns out that you can rewrite this boundary term exactly as a particle action, as the world line action of a particle that has some spin. So in this particle action, we have a kinetic term and a spin term. And the spin term originates from this boundary curvature. And the spin of the particle is related to the value of the dilaton at the boundary of spacetime. So because this particle lives on a rigid spacetime, rigid 2D spacetime, it can be quantized exactly, analogous to a free particle on a real line, just in elementary quantum mechanics. So the analog of the real line here would be ADS2, and the analog of time is the proper time of the particle. And the main quantum observable is the position of the particle in ADS2. So we saw that there's a clear equality of actions between JT gravity and the boundary theory, sort of almost trivial because the bulk action vanishes. However, there is a non-trivial holographic duality here, which is between the dilaton solution to Einstein's equations, which came from varying the bulk action with respect to the metric, and the total, if you like, evolution of the boundary particle system in some quantum state. So more precisely, we know that if we tune the state of two particles in such a way that each particle is in a thermal state, and if we take the limit of the spin of the particle being large, so in microscopic language, going back to the SYK model, this would be the limit of a large number of fermions. And if we take the temperatures to be low, this evolution of the boundary system is somehow dual to or reflected in the dilaton solution to Einstein's equations.
Sorry, I have a question. When you reduce to boundary dynamics, you are solving the system without matter, I imagine, or does it also? Yes,
but you can easily think of coupling matter sort of kinetically to this boundary particle. Yeah.
Thank you.
Yeah, so to date, we know that this duality is of a nature such that information plays an important role, and the Rutakanagi Formula sort of captures that in a nutshell. And in this simple instance, I mentioned the formula earlier, but in our simple context, the formula says that the extremal value of the dilaton, which is at the horizon of the dilaton solution, is equal to the quantum entropy of the density matrix, the thermal density matrix of one particle. So a preview of my results. So as advertised, we will deconstruct this duality. And meaning we take apart this gravity theory and directly derive Einstein's equations from the quantum theory of the boundary particle. And we show that the solution to Einstein's equations, which is the dilaton or the area of the sphere at a point, is actually equal to a stationary probability for a particle to be at that point, where stationarity is defined relative to a Markov process induced by the quantum evolution of the particle and its density matrix. And all of this is accomplished in the setting of JT gravity, but we can hope essential features of the mechanism of how gravity originated from the quantum theory, such as emergence of space from probability, there being a Markov process, and Einstein's equations expressing stationarity with respect to that Markov process. We can hope those features actually lift to more general / higher dimensional theories of gravity. So yeah, any questions at this point?
One question is about the holographic duality in say, the four-dimensional example in ADS5 CFT4, the whole the dual theory, the CFT has some large n. But in this case, maybe I missed it. It seemed that what you did was actually to solve the constraint in Einstein's equations and get a formulation of Einstein's gravity in terms of a single boundary degree of freedom. So there is no large n, right?
Yeah. So that kind of got. So there was a passage from my microscopic description of the quantum model, which involved actually a large n, because there are a large n number of Majorana fermions. So we passed from that microscopic theory to an effective low energy theory, which just involves particles. So the large n gets sort of packaged into this coefficient of the action, which is the boundary value of the dilaton. And in this formulation, it actually enters the spin. So this spin is actually proportional to the large n parameter in the microscopic theory. Yeah. Yeah. So I'll move on to discussing some basic notions in stochastic processing.
Can I ask a question?
Yeah.
Yes. So I think it seems that you're working in Lorentzian signature, and you are doing kind of canonical quantization of the quantum theory of the particle in the boundary that is attached to that W mu with this kind of, I don't know, like a gauge field or something. I mean, if the particle would be charged, that would be the action. But is there a contradiction with Stanford, Schenker, and Suh, which say that the duality of JT is not one quantum theory, but is basically an ensemble of quantum theories on the boundary?
Yeah. So, the story of there being geometries of non-trivial topology, that actually applies to corrections that are suppressed exponentially in large n. So there have to be special situations where those very exponentially suppressed effects become important, and there can be such situations. But generically, in this action, we've ignored such exponential corrections. So in this quantum theory, we're thinking about powers of n, effects so the quantum theory of the particle captures effects that go as powers of 1 over n, but don't include e to the minus n effects. Yeah. So I have to introduce some basic notions in stochastic processes in order to give you the analysis. So we have to define what a probability space is. So a probability space has 3 components: a set of outcomes, subsets of those outcomes, and a probability function acting on those subsets. So the subsets correspond to events, and the probability function is giving a number for each event. And the first 2 components only, they constitute a measurable space, which is a slightly more relaxed notion than a probability space. And a random variable, so once we define a probability space, we think of random variables defined on that space. So this is a random variable is a map from a probability space to some measurable space, such that the pre-image of an event in the target space is an event in the probability space. And this means that the random variable can induce a probability distribution in the target measurable space. For example, the distribution on some event B would be the probability function in the probability space acting on the inverse image of B. And a stochastic process is actually just a collection of random variables indexed by some set T, taking values in a common measurable space. So we can think of this index set as a collection of times. So a stochastic process is, it's consisting of a random variable at different times. And so this is a natural framework for analyzing dynamical systems. But unlike in traditional physics, where the focus is on the evolution of matter, the focus here is on the evolution of probabilities and associated information. So an object of interest would be, for example, a joint probability distribution for the variable, random variable at some time t1 to be in some event b1, and the variable at a different time t2 to be in some different event b2, and so on. And once we have such joint probability distributions, we can compute things like the entropy added per each additional random variable, because we have a probability distribution. And a Markov process models deterministic dynamics. So the value of random variables at a given time determines the distribution of random variables at all future times. So this is a particular type of stochastic process. And here, I have a picture depicting the Markov property. There's a linear transfer of information between times. And this is an example of how the Markov property could fail. If you had an external bath that determines the variable at some time, but also influences the variable at the next time step, this is not Markov. So what will be relevant for us is a Markov process indexed by one continuous parameter. And such a process is defined by a chain of joint probabilities produced by iteration of a probability kernel. So a probability kernel here is just a conditional probability for the random variable at some time s to assume value y, given that at a previous time t, it assumed some value x. And a joint probability in such a Markov process, a generic joint probability, is given by a product of conditional probabilities acting on an initial probability distribution. So this is sort of the mathematical definition of a Markov process indexed by one continuous parameter. And the following will be important for our discussion of gravity, which is that the probability kernel induces a Markov operator acting on probability distributions. And this is just the fact that given some distribution nu, we can integrate it against the probability kernel and obtain a distribution at a later time. And the Markov operators form a group for which a generator can be defined, which is a time derivative of the Markov operator. So essentially, we differentiate the time evolution of a probability distribution given by the kernel. And because this generator is a linear operator acting on a space of functions, i.e. probability distributions, it often manifests as a differential operator, which can be obtained from this kernel. So the connection to gravity will be that once we define a Markov process and obtain this generator of the Markov process, that generator will be the differential operator that appears in Einstein's equations. So just to show in a very simple example how how we can get a differential operator from this setup. If we have Brownian motion, also called the Wiener process, in which we have a random variable with independent increments between time, each of which follow some Gaussian distribution with given by the time difference, the probability kernel takes this Gaussian form with width given by time. And the generator we can obtain by differentiating the action of this probability kernel on nu, a probability distribution. So you see that in this integral, we have this kernel, and then we change variables so that the time dependence is shifted to the argument of the probability distribution. And then we expand this argument and then perform the integrals. And so the end result is that the derivative of this action, or the generator, is given by this second order differential operator acting on the distribution.
Sorry, Josephine, just to make sure I'm following. So you said that the differential operator that appears in Einstein's equations can be thought of as this, but I mean, that differential operator is a partial differential operator.
Yeah.
Right? So there's time and space. And the way you're presenting this here, it's a Markov process of time. So where does what role does the derivative in space play in thinking about this?
Yeah. So yeah, what's relevant is that so we had a particle, and essentially the scheme is that we treat all of ADS2 as essentially space, and the time that we're talking about is the proper time of the particle. So this time that we use to define the one parameter Markov process, that will be the proper time of the particle, and we'll have a differential operator basically in 2 dimensions, or on ADS2.
Okay.
Does that answer? Yeah. yeah, so the scheme of deconstruction will be, we'll first extract joint probabilities for the boundary particle to be at some location at time t1, and another location at time t2, and so on. And then we'll show the joint probabilities define a Markov process, i.e. They're produced by iteration of a probability kernel. And then we'll derive the generator of that Markov process from the probability kernel and see that Einstein's equations are actually expressing the vanishing action of that generator of the Markov process on the dilaton. So this means that we can identify the dilaton solution as a stationary probability distribution of the Markov process generated, induced by the boundary particle. Yeah, so as I mentioned before, all of our discussion about probabilities, stochastic processes, and so on was in the setting of classical probabilities. And we actually have a quantum system to deal with. So we need to adapt some of the notions that we discussed to a quantum setting. So a quantum probability space actually has analogs of the three components that we discussed before. So the analog of the set of outcomes is actually the Hilbert space. And events or subsets generalized to projections in the Hilbert space. So each of these projections correspond to an event. And probability function, this is generalized to a density, to the density matrix. And so the rule for computing a probability for an event corresponding to a projection is that, of course, we take the trace of the density matrix with the projection. And we also have the quantum analog of random variables. So that analog is an observable, which takes values in some measurable space. So we are trying to define an observable in a slightly different way than we do usually. So here we define an observable to be some function from subsets in a measurable space to projections. So it's actually a projection valued map xi from subsets in a measurable space to projections in a Hilbert space. And if you think back to the definition that we had in the classical setting, this map xi is the analog of the inverse random variable x inverse, which mapped some event to some event in a probability space. So here an event is being mapped to a projection. And this definition is actually inclusive of our usual definition in quantum mechanics, because a self-adjoint operator, a Hermitian operator, is in one-to-one correspondence with a real valued observable by this decomposition of the operator into projections onto spaces spanned by eigenvectors of the operator. So, so this was just to sort of think about the usual rules of quantum mechanics in a slightly different way that will help us define this Markov process in JT gravity. So we finally get around to doing that. So I'll describe a Markov process in JT gravity. And so we have to get oriented, first of all. So the emergent space-time ADS2 is actually a measure space in which the observable, the position of the particle, takes values. So we can view ADS2 in this way. And then the volume measure of ADS2 is in fact a probability measure because it enters the inner product of wave functions for the particle, which is an integral over ADS2. In other words, it weighs probabilities. And the projection valued measure corresponding to the observable is actually just the projection onto the space spanned by eigenvectors of X. So we would like to define a one-parameter stochastic process consisting of the observable at different proper times. So we can start with a simple probability for a particle to be at some position x1 at time t1. And assuming the density matrix of the particle is rho, this is given by the trace of rho multiplying this projection operator. And to define a classical stochastic process, we actually need to go beyond this and have joint probabilities. But it turns out that in a quantum system, we don't have exact joint probabilities. The closest analog we have is the expectation value of a product of projections.
Can I ask you a question?
Yeah,
Just
yeah.
So on the previous slide, when you said ADS2 was the measure space, It's just a postulate of the construction, which will be kind of checked afterwards. Is that how the logic goes, or was it derived somehow?
Well, this is sort of it's sort of a fact that is true. It's it's just it's an observation, I would say, because we're sort of looking at ADS2 from the point of view of the boundary system. So from the point of view of the particle, it's just manifestly true that ADS2 is a target space for an observable, which is the position of the particle. And the fact that it's a measure space just means that we can interpret the volume measure of ADS2 as a probability measure. And this is also sort of manifestly true because this volume measure naturally enters the inner product of wave functions for the particle. So we sort of, yeah.
When you said it was target space for a particle, so you introduced the target space in your action for a particle somehow, or you wrote the action for a particle. I didn't notice that you. Yeah.
So this action is a world line action.
Right. Oh, okay. Here is the that G mu nu is your target.
Exactly.
So it's in there. Put from. Okay, got it.
Yeah.
Thank you.
Right. So I was discussing joint probabilities, and I was referring to the fact that in a quantum system, we don't actually have exact joint probabilities. Instead, the closest we have are these expectation values of a product of projections. And so, a single projection operator is positive by definition, but a product of projection operators is neither positive nor Hermitian. So although these EVPPs, I call them the expectation value of a product of projections, these integrate to one because of completeness of projection operators. In general, they are neither real nor positive. So we cannot interpret them as classical joint probabilities. But for our purposes, it's actually sufficient to extract from these EVPPs consistent joint probabilities in the classical limit. And it turns out that in our quantum particle theory, if we, there are some assumptions that go into this, like, we assume a thermal density matrix for the particle, and we take an appropriate limit of parameters, and we restrict the time scales for the particle. So after doing this, we can identify effective joint probabilities that appear in the classical limit of integrals involving the EVPPs. So the idea is that we use the EVPPs that I've defined here, we use them as if they were joint probabilities. And then in all relevant integrals, in all integrals involving those EVPPs, we can evaluate those integrals in the classical limit. And they look like, we evaluated the integral with proper, with actual joint probabilities. So I'll try to explain that a little better. So we use the saddle point approximation in these integrals. And because the saddle point approximation fixes the integrand to have constant phase, we effectively get an actual joint probability, which is positive. So this is how we identify the joint probabilities that will define our Markov process. And we can ask, do they have the Markov property? Can we express these effective joint probabilities in terms of probability kernels, like I showed you earlier for an actual Markov process.
Sorry, Josephine, I'm so sorry to interrupt again, but just to try to understand. So, what you're talking about right now is very general. You could try to define this joint probabilities in quantum mechanics for any quantum system. There's nothing about holography or ADS here. Has this been done before, or is this your own work? Where does this fit?
So obviously the definition of a Markov process is something that you can find, in a book on probability theory, but to try to apply it in this way to a quantum system, as far as I know, I just did it on my own.
Okay.
Right. So there are some subtleties. Of course, people have wondered about the general question of how do we define a quantum Markov process? And but in the literature, you'll see that they kind of got lost. For instance, they try to define it in such a way that if you have an expectation value of a product of projections, they try to require that this is always positive. But that's not what we're doing here. We are saying that it's sufficient that in our system, we'll analyze these EVPPs, and it's sufficient that we can extract joint probabilities in the classical limit. So that, to my knowledge, hasn't been done before. And
sorry, I'm asking, so this part, does it rely on the fact that particle moves on a DS2, or you can do it in principle for any geometry?
Well, yeah, that's a good question. So yeah, this is part of what I'll describe on the slide. So when we require that these effective probabilities that appear as a result of integrating these EVPPs, when we require that they have the Markov property, that's actually a very specific requirement on the actual propagator of the particle. So because you know, the Markov property is saying that we need some factorization of the effective probability. So if we start with an integral of an EVPP, which involves these this product of propagators, so that this is derived from the quantum particle theory. And we're saying that in the classical limit, this product should factorize into some Gaussian packets. So this is a very specific requirement. And it turns out that even in this particle theory, to satisfy this property, we have to go to some asymptotic limit. So it's crucial to use the asymptotic form of the particle propagator and the geometry it probes in the limit that the proper time in the limit of the proper time of the particle being very smaller than the ADS radius. So in this limit, the particle doesn't travel for very much. So, you know, if this is global ADS2, so it travels over very short distances compared to the ADS radius. And we kind of zoom in to these short distances so that the geometry effectively looks flat. And yeah, so the point is that the Markov property is only satisfied when we use the propagators in this limit of very short proper times appearing here. So it seems to be a somewhat fine-tuned property. Although, you know, Markov property is stated generally sounds very generic, we've translated to a very specific statement. And so after checking that we do actually have the Markov property in this limit, we can look at the time evolution of a probability distribution. So that's given by this 2-point EVPP, which corresponds to the probability kernel. And if we take the classical limit, we can see that the probability at a time is actually the sum is given by the sum of probabilities at a previous time that is separated in distance by some distance that the particle travels over the time. So what happens is that the saddle point actually depends on the time. And the saddle point approximation is telling you that the probabilities traveled over exactly the distances that the particle travels and sort of evolves straightforwardly in that manner. And so if we consider the generator of this time evolution, meaning that we take the time derivative of this EVPP or probability kernel, notice we have to take the time derivative before applying the classical approximation because the saddle point itself depended on the time. So we take the time derivative, and here we have this formula, and then this is a somewhat subtle calculation, but I won't go into much detail, but you get a differential operator acting on the probability distribution, just like happened for Brownian motion. And we see that it can be related to the differential operator in Einstein's equations. Yeah, so from this, we conclude that Einstein's equations are actually solving for a stationary probability distribution of the Markov process induced by the boundary particle in a thermal state. And in particular, the dilaton solution, which is the area of the sphere at a point, equals a stationary probability for a particle to be at that point. And a somewhat subtle aspect of this statement is that it doesn't specify which matter realizations of the particle contribute to the stationary probability at a point. It just gives you the probability, but it doesn't say, you know, how many particles there have to be in order to realize that probability. And that is actually something that's determined by the solution itself. So for instance, in the vacuum solution to these equations, we have two causally disconnected regions. So the probability in each of those regions cannot mix with each other, so have to be due to two distinct particles. And so I've denoted them blue and pink particles. But the probability inside the horizons is actually coming from both of those particles, because the insides of the horizon are connected causally to the outside of the horizon. And so the probability inside the horizon is qualitatively different. It's a probability for either the blue or particle to be there, as opposed to outside the horizon, where the probabilities is due exclusively to one particle.
Can I ask you a question?
Yeah.
On the previous slide, when you said it's related to the Einstein equation, I would be curious to see how the tensorial structure emerges. This relates to my first question.
Yeah. So it's somewhat technical because we use some coordinates, but I think I can say that this is a linear combination of the differential operator in Einstein's equation with some coefficients that are also coordinates and are vectorial. So if we require that this linear combination vanishes, because the coefficients in the combination are coordinate dependent, if we require that they vanish everywhere, then we get a tensorial equation.
So you just stripped off the coordinate, which probably contracts this operator?
Yeah.
Can you, I didn't quite understand what you meant about two different particles. I think what you're saying is that these two wedges are causally disconnected. But why can't you have a probability distribution for a single particle that has support on both of two causally disconnected wedges? Why does it have to be two separate particles?
Yeah, so what we get is a stationary probability distribution, and then it's a separate question as to what matter realizations of the particle actually realize that probability distribution. So what I was saying was, if you have a distribution in this wedge, and if you have a probability distribution in this wedge, they have to be coming from two distinct particles, because a particle in this wedge cannot travel to the other wedge.
But why can't I just have a distribution that says there's, whatever, a 50% chance for it to be in the pink wedge and a 50% chance for it to be in the blue wedge? Why does it have to be two particles that are distinct?
Yeah, so suppose you had some particle in this wedge, then it's never going to travel to the other wedge, right? So that means a probability in this wedge is coming from a particle, and the probability in this wedge is coming from another particle, but they're not coming from the same particle, because a particle in this wedge cannot travel to the other wedge. It's sort of a causality argument.
Maybe it's a question of semantics. I don't really understand, but okay.
So my ask also here. So Einstein's equations, well, this is equations of classical gravity, but eventually we want to talk about quantum gravity. So what does it mean in this language? What quantization of gravity, what does it mean in the language of these probabilities which you introduced? And
yeah, that's that's a question that I'd like to, that's a research question for the future. But I think we can try to generalize the definition of a Markov process such that it doesn't rely on classical probabilities. And people have tried to do this in certain instances, but I think you can try to do that, and it involves things like operator algebras, and hopefully there's some generalization of what it means to have a Markov process, and then we can think about generalizing what we have found here to a full quantum system.
But you already took a limit in order to make your joint probabilities real, right? So if you take that limit, then what? I mean, then these probability distributions would be complex or something.
Yeah. So that's exactly right. So I had to take a limit to get these joint probabilities. So the idea is that the Markov process is defined using those joint probabilities only in the classical limit, and away from the classical limit, hopefully we can have another definition of there being a Markov process.
Okay.
Yeah, so I'll summarize and discuss some further questions. So it has been known that a gravitational theory can quote unquote emerge from a quantum system in one less spatial dimension. And what we have done is, in a simple example involving the SYK system in a lab, we have shown that the emergent space-time in Einstein's equations are actually manifestations of probability / dynamics of probabilities associated with some observable of the quantum system. More concretely, we've sort of demystified holographic duality in this case as a mapping between probability spaces. So quote unquote emergent space-time is actually the target space for an observable, and solution to Einstein's equations is actually a stationary probability distribution on that target space. And these together form a classical probability space. And the mapping from the quantum probability space involving the Hilbert space and density matrix of the quantum theory to this classical probability space, it's mediated by a Markov process induced by the dynamics of the quantum system.
But when you say emergent, I guess you mean something else, because it was placed in there already in the world line action, as you mentioned, right?
Yeah. So so when I say emergent, I mean, we started out with a 0 + 1 dimensional quantum system, and it's only when we think of the target space for an observable. So this observable you can just think of as an operator in the 0 + 1D quantum system. But it happens to have a target space that coincides with what we think of as emergent space-time in our usual ADS-CFT picture.
But the space was put in there to begin with. I mean, target space you postulated.
So it emerges from the quantum system in the sense that there happened to be this special quantum system, the SYK system, that had an observable in it, for which I guess there was this, there is this observable that has a target space with a probability measure that actually coincides with, two-dimensional anti-de Sitter space. So in some sense, it was built in because we started out with the right quantum system. We knew this quantum system had a gravity dual. So yeah, it was built in that sense. But more generically, if you had some arbitrary 0 + 1D quantum system, you could think of an observable, and it would not have an ADS2 as its target space. But yeah,
I think maybe Greg's question is in the point particle action that you wrote down, there was G mu nu. Was that G mu nu ADS2 to begin with, or is it the solution to some equations and it then becomes ADS2?
Yeah, it's fixed to be ADS2 because of the action of JT gravity.
Right.
Yeah. Yeah. So some questions that I'd like to think about in the future. So what we found sort of gives a context for the Ryutakenagi formula. So the Rutakanagi Formula is a statement about special values of area in a gravitational theory, the extremal value of area. And we've found a characterization of all values of area. So can we derive the Ryutakenagi formula from our characterization of Einstein's equations? So this is one question. And another question is, we would like to include the energy momentum tensor in Einstein's equations. So we know that this characterization of the dilaton as a stationary probability configuration continues to hold in the presence of matter. And this is because we can sort of easily see that this property that the level curves of the dilaton coincide with classical trajectories of the particle, this property continues to hold. So it seems as if we continue to have, we should be able to continue to express Einstein's equations as the vanishing of a generator of a Markov process. But what is the probabilistic interpretation of this extra term in the generator, which is the energy momentum tensor? So that's a question that I'd like to answer. And so somewhat relatedly, we would like to sort of relate two variational principles that appear in seemingly different form. So in our analysis, we derived Einstein's equations by identifying a Markov process, obtaining its generator, and then expressing stationarity of a distribution with respect to that generator. But of course, in the action formulation of general relativity, Einstein's equations express the stationarity of the action with respect to metric variations. So we want to relate these two different variational principles and directly interpret the action and metric variations of a gravity theory in a probabilistic framework. And we hope the notion of Markov processes could be powerful enough to go beyond JT gravity and encompass more general / higher dimensional theories of gravity. And one reason to hope that this is possible is, for instance, in the presence of a potential for the dilaton in JT gravity, Einstein's equations become nonlinear. But correspondingly, there exist nonlinear Markov processes in which the future depends on the present probability distribution as well as value of a random variable. So, and finally, we would like to extend the analysis that we had to be able to capture the full quantum theory that we begin with. So we recast holographic duality as a map from a quantum probability space to a classical probability space. And in particular, the map relied on identifying a Markov process defined using classical probability distributions. And we would like to extend the notion of Markov processes so that it applies to quantum systems beyond the classical approximation. And this is because we hope a satisfactory answer could give further insight into gravity. So in the map that we had, if we replace the word classical with quantum everywhere, maybe we would have a new characterization of quantum gravity. Yeah, so any questions at this point? I'll move on to my, yeah.
I have just, well, one question is that when you have matter, like in the SYK model, actually, you have a very non-local matter, right? So the matter of the sector is very complicated. Then the metric, the G mu nu metric, isn't it dynamical? It's no longer fixed to be ADS, right?
Yeah, that's that's right. So, I worked with JT gravity, which is the leading action. If you write down the effective action for the entire SYK model, it's the leading term in an expansion in low temperature. So it's a double expansion, both in large N and low temperatures. And so if we go beyond this approximation, then we'll basically have a more complicated gravity theory where the metric is no longer rigid, it's dynamical. And so, so basically the probability measure won't be fixed, it'll be fluctuating. And so it seems like we'll just have a more complicated problem. Fluctuating probability measure, as well as, I guess, the dilaton equations become nonlinear. So, but the fact that there also seem to be these nonlinear Markov processes, gives hope that we can try to capture that nonlinearity, or at least we can hope to try to capture such nonlinearity in the framework of a Markov process.
Thank you.
Yeah. So finally, I'll give some outlook for the future. So there seem to be some opportunities to reformulate classical gravity and discover new relations between gravity and quantum physics. And the broad strategy that I've outlined is that we can try to build connections to probability theory and stochastic processes in the setting of quantum systems. So we've identified an arena and a set of questions that are sort of wide open for exploration. So it feels like it's an exciting time to be a theoretical physicist. So thank you for listening.
Thank you. And now it's time for questions, more questions from the audience, so please.
So it's related to what I was trying to ask before, but so if I started instead of JT gravity, which you have, if I started with JT gravity where constraint puts rigid space to be flat rather than ADS2.
Okay.
How much? It looks like the rest of your story would stay the same. The relation, you would get still the same Einstein equation. So how would what would change?
Okay, yeah. First, I'd have to check that let's see. So, yeah, first I'd have to check that there was a Markov process. So that's
yeah, that's why I was asking you. So yeah, where you were, because it sounds like actually your Markovian property relies on zooming in, as you were saying, on the flat space limit. So then if metric is actually fixed to be that flat, then it sounds like it should be even better.
Yeah, so that limit is a bit subtle because let's see, I want to go to that slide, sorry. Let's see. Oh, yeah, so we're zooming in so that the metric is flat, I think, to first deviation, so to first order in deviation from the point. So I think we're retaining some curvature, and I'm actually not sure to what extent, if we just had flat space, I'm not sure. I think I would want to check explicitly whether, you know, everything that I said holds, like the Markov property that, you know, if you had these product of propagators. So actually, if you had flat space, let's see. I mean, would you have a,
Because there's a reason I'm asking that actually in flat space, it's, well, in the presence of T mu, actually, the full quantum level, it is known what this does. This describes also what's called recently TT bar deformation. So this kind of interaction with particle changes the S matrix of the theory which lives in the flat space and deforms in such way that it's equivalent to TT bar deformation. But yeah, but I'm having trouble to establish kind of any connection between that piece of knowledge and between what's happening in your talk and with these Markovian processes. But
okay.
Yeah.
So I guess to have flat space, you would erase this term.
Yeah, just basically erase this too. Yes.
Okay. Yeah, so the curvature term would look different in flat space, this boundary curvature term. So I wonder if you can actually turn that curvature term into an action for a particle.
Yeah, it does become action for a particle.
It does? Okay.
Yes.
Okay.
Yeah.
Yeah, so then that's interesting. So I guess I can just go through the same motions here. And I guess, yeah, the question is whether we'll have this Markov property. Yeah. Yeah, so I think everything about the physics of the particle is actually contained in this EVPP, these expectation values. So the form of these propagators and the density matrix. So maybe, yeah, maybe it'll still hold. Yeah, maybe it'll still hold. So yeah, one thing that I didn't mention is that so you have to, yeah, maybe it'll still hold. Yeah, that's interesting. So maybe we can derive Einstein's equations in flat space. Yeah.
Could I ask about higher dimensions? So what would be the analog? I mean, so here you started with JT gravity, and then there was this kind of low energy effective description at large n, which was this point particle action, if I understood correctly. So if I start with something, excuse me, with something like n equals 4 Yang mills, is there some analog? What would it be?
Yeah, so I think, so I talked about this effective particle theory, but I think for all intents and purposes, what you can think of as sort of, what you can take away, what you can abstract away from this is that we have an observable, and we think about the target space for that observable. So I suppose if we were smart enough to identify this observable directly in the this operator that corresponds to the position of the particle, if we were smart enough to identify that directly in the microscopic SYK model, we can just as well talk about everything that I talked about, because, you know, we have, all you need are these expectation values. So let's, yeah, what I call the EVPPs. So yeah, so we have these traces or expectation values of projections corresponding to that observable. And we can compute these EVPPs and, you know, extract a probability kernel and think about this stochastic process happening on the target space. So, yeah, that's the abstraction.
So are you saying that in n equals Fourier-Mills, there should be some operator which we can think of as representing the position of a particle in ADS5 times S5, or just ADS5, or what?
Yeah, so yeah, I guess, yeah, now you're going into more specifics. So yeah, I think we need to think about observables, some operators, but, you know, of course, if you go to the higher dimensional case, you don't want, well, you have more degrees of freedom. You know, the bulk metric is fluctuating. So I think what, yeah, it's related to the questions that I had at the end. But I think the way to think about higher dimensional theories will become clearer if I am able to make this connection between the variational principle, the way that I found Einstein's equations, and the actual action formulation of general relativity. Because the main difference in higher dimensions is that you have these tensorial quantities, these, instead of having this compactified space at each point, which is a scalar quantity, you have tensorial metric fluctuations. And, but I think they should be related to operators in the quantum theory. In the same way, you know, so yeah, so basically there should be some analog of the position of the particle in some general sense, yeah.
But shouldn't then your probability distribution be a tensorial quantity in, let's say, in 4 dimensions, if one were to do something like this?
Yeah, so I think what can actually, so the concrete statement that I expect will be generalized is that, you know, the volume of emergence, the volume measure, or the area of a codimension 2 surface is a probability. So here we're talking about scalar quantities. We're talking about the area of compactified space. Those are all, you know, and that's why we could make the connection to probabilities. And I think if you go to higher dimensions, you'll have analogous statements concerning the area of a codimension 2 surface. So the area of a codimension 2 surface may be a probability corresponding to some observable. But if you want to think about the actual metric, you know, the form of the metric that from which you can calculate that probability, I think that requires more detail. So that's the part that I don't have yet. But you can easily think of statements relating area to, or volume, relating that to probability. You can easily imagine how, you know, that those could be generalized.
You have other questions? I have actually one general, one technical question. So the general question is that stochastic processes have appeared in 2 areas in quantum mechanics. One is in stochastic quantization that was used in gauge theories, where you have stochastic processes and Langevin equations, etc. The other, maybe it's more related to this, is in the process of continuous measurement, when you want to describe
yes,
measurement.
I come across that, yeah.
It's there, because even there you have Markov processes, you have a stochastic process, you have more generally weak measurements, so you don't use projection valued operator measures, but positive valued operator operator measures. So my question is, do you know of any connection between your work and the work done in non-gravitational settings, in continuous measurement or in the stochastic quantization of gauge theory? And the technical question is why projection valued measures and not positive operator valued measures?
Positive operator valued measures.
So when you do a weak measurement, right, I mean, you can express the result in terms of Krauss operators, right? But
I see, yeah,
not
yeah.
in terms of projections. Well,
Yeah.
weak measurement means that you do a strong measurement on a system that is weakly coupled to what you want to measure.
I see, I
The
see.
result can be just a positive valued measure, not the projection valued measure.
Oh, I see,
That's
I
the
see.
technical part. But the more general is whether you have seen connections between your work and this whole area.
Yeah, so I did come across that literature on measurements, and so the relation to my work is that I don't want to have measurements on my system, right? So I want to talk about a system that is not measured, that is unperturbed. So in some sense, I had to sort of I had to think of a way to use projections, but not in the context of measurement. So here the density matrix is not being modified by my projection. Yeah, so I had to think of sort of a way to talk about joint probabilities and such without talking about measurements. I guess that's the connection. At first I tried to think about, I thought that I had to have something like, what people discuss in the literature of measurements, that somehow I would be able to find consistent joint probabilities that correspond to having made multiple measurements on the density matrix. But I concluded, yeah, I mean, when I passed Einstein's equations, I don't want to be thinking about measurements that change the system. I actually want to think about the full quantum theory. I think, and then you talked about positive valued, was it positive valued operators?
What is
POVM, positive operator value measurements.
So yeah, these projection operators, I use them because they sort of naturally correspond to events in this formulation of a quantum probability space. Yeah, that's really the simple reason. And I don't know if, let's see. So what is the difference between a positive valued measure and a projection valued measure?
Well, that you don't have a projection in general. You have if you want a sum of projection weighted by a positive coefficient.
I see.
A projection would be, say, take a density matrix and multiply left and right by some operator, some projector, right, that puts on a state. But you can also take this density matrix and do a projection over state A with weight alpha A.
I see. Yeah.
Different.
So at this level of discussion, that generalization doesn't seem to be necessary. Yeah.
Because for continuous measurement, they're sort of natural. They come out.
Yeah.
I wondered if it was also natural here, since at some point you take a continuous limit in T.
Yeah, so the nice thing about this mathematical sort of formalism of a Markov process in a continuous parameter is that it led to this generator. So we can always talk about joint probabilities at discrete times, but we can use this generator that to think about the continuous process. So I think there are actually some mathematical results that say that we essentially exponentiate this generator to obtain the entire time evolution. And then, yeah, the probability kernels relate different joint probabilities over discrete times. And then to capture the entire continuum, we use this generator. Yeah. Yeah, I think that's very interesting what Sergey pointed out about flat space. So it seems like this might just go through, but okay.
I should say there is a, yeah, because the action for particle which one gets in that limits, it's not kind of conventional point particle action. It's more like Chern-Simons. It's one-dimensional Chern-Simons action. So
Okay.
actually, that's really a bit. So because usually people work in coordinates where this in your case when this action for particles that's described by Schwarzen. So so what your action is not.
Yeah. So you can't use the Schwarzian. So that's a point that I can explain. So the Schwarzian actually applies at relatively long proper times for the particle. So it actually applies in the regime where the particle, if you place the particle at a point here, if you wait sufficiently long, it'll move to close to the ADS2 boundary. So this is when proper times are large compared to the ADS radius. That's when the Schwarzian action applies. So what we have to do is actually start from the exact particle worldline action that is not the Schwarzian action. And then we derive this propagator that applies at short time scales. So yeah, that was an important ingredient to what I did, yeah, to figure that out.
Thank you. There is just a question from Glennis. This forthcoming paper will be by you and would be by you alone or would be with?
Yeah, it'll just be me, yeah. Working alone during the pandemic.
Thank you. Any other questions?
I had one more maybe about this slide. So you took the small time limit because otherwise your probabilities wouldn't factorize properly. But can you in some sense take the first correct? So what you say is the stationarity of this probability distribution is equivalent to the stationarity of the Einstein action. So you get Einstein's equation out. But can you also get higher corrections? Let's say a higher next order corrections to Einstein equations from this by, let's say, expanding in TB over R or something like that, or that doesn't work?
Yeah. What do you mean by next order? So in
let's say the R squared coefficient, the next order coefficient for higher curvature invariance.
Yeah, I don't know. So are you thinking of a generalization of the theory that we had?
Yeah, I guess it would not be called JT gravity then anymore.
Yeah. So you would have some extra terms, I assume, here on the boundary, in the boundary action as well.
Yeah, sorry, I'm not an expert. I'm not sure what if the higher order terms vanish in JT gravity or not. It's kind of a special system.
The higher gradients of phi, right?
Yeah. Yeah. So normally what happens when you is for more general theories that you can essentially, the examples I've seen, you can sort of package them into like a potential appearing to the dilettante. I mean, that's one way you can have corrections to this. I don't know exactly what kind of corrections you're talking about.
Yeah, I wasn't sure if there's anything to be gained from just going beyond taking first derivatives, but yeah. Not a deep question.
Yeah. Yeah.
Can I ask, this is a naive question. Is there a relation to the work of Van Ramson where he kind of obtains the linear Einstein equations on the ADS side, basically from the first entanglement, basically from the first law of thermodynamics?
Yeah.
Is there a way to understand your work to the stuff he was doing? Is there a parallel?
Yeah, I don't see a direct connection because, yeah. So before, I think previously people have tried to derive Einstein's equations using entropy, right? And so here I'm using probability. a slightly different point of view. But I think it's really interesting to think about how we can derive the Rutakanagi formula from what I had here. It's not straight. I thought it might be straightforward, but maybe it's not. It's the connection between the two is, I don't know, it doesn't seem to be so trivial.
I think there is a question in the chat.
Okay, let's see. Okay, how do I? Chat, okay. Oof. Okay, can you explain a bit more about your big picture hope for this? Would you, for instance, find some restriction or find a quantum theory? Who is this from? Can't see. Okay.
This is from Glennis, I think.
Okay. Yeah. So big picture is I think basically I want to pass to understanding the action formulation of GR or gravity theories in general in this probability language. And I think, yeah, so we'll go from there. So once we have that, so that's kind of at the classical level, you know, the next question is really, I think, a big challenge to try to generalize to the quantum level what we have. Some restriction on possibly emergent spacetimes, or find a quantum theory of gravity. Yeah. So find a quantum theory of gravity. Yeah.
I guess another way to put the question would be, so it's a fascinating connection, and especially the aspect of probabilistic and whatnot, which it looks where, you know, starting from something that looks so not probabilistic. Mm-hmm. And so I just was curious what it might lead to. I mean, for example, supposing a certain one you couldn't do, would that tell you something particularly interesting, or you just couldn't do it? Or do you think you would find, I wish you'd talk a little more. Of course, that's asking you to dream too far in the future, probably.
Yeah, so maybe what we've been, maybe what we've been thinking of as gravity is actually, you know, maybe it's a theory of probabilities, you know, because this, so in this duality, for instance, you know, we had an identification. We said that the emergent space-time is actually a target space, and the volume measure on that space-time is actually a probability measure. So, I mean, it's easy to think of there being a space and then there being some probability for some degrees of freedom to be in that space, but is it that the probability comes first? You know, so is the probability the more fundamental quantity here? And this goes back to the fact that we had this duality to try to explain, like if we had a 0+1D quantum system in the lab, you know, why do we have a gravity dual to it? You know, where is that gravity dual appearing? And I think, at least in that simple example, we were saying, actually, the gravity dual to that system that we have in the lab is a target space where we have these probabilistic dynamics of probabilities, and Einstein's equations are a statement about, you know, a stationary probability distribution. So we're saying emergent space is actually a probability distribution. So it seems like the probability distribution came first. That's what we know how to derive from the quantum system. And then that's actually, you know, that's actually what we think of as space. So maybe probability is more fundamental than, you know, space.
Well, maybe one follow-up to that question and to Sergey's earlier one. So in some sense, Sergey suggested erasing the +2, right? And looking at the flat space case. If you replace the +2 with a -2 and look at the de Sitter case, then maybe something strange, you know, that probably there's no well-defined quantum theory of gravity that lives only in de Sitter. So it might be interesting to see if something changes in your analysis.
Yeah. So in that case, do we have, so I guess I would again ask, like, can you turn the boundary term into a like a particle action?
Yeah, there might not be one in that case because it's closed. So that might be wrong.
Okay. So there's no boundary.
Well, there doesn't have to be.
Okay, there doesn't have to be, yeah.
But one can introduce boundary by hand, essentially saying that it's de Sitter with a boundary. And
Yeah, okay. Yeah. Yeah, so it's interesting, maybe, maybe this is like a probability, talking about probabilities is a way to sort of generalize, maybe it doesn't have to be restricted to the, anti-de Sitter case.
Sorry, but here, isn't space-time introduced already by hand? I mean, if I had a quantum system, so instead of X, I had another quantum system, electrodynamics, etc. I could have defined joint probabilities, etc. And what would I get in that case from this procedure? There would be maybe some observable that mimics space-time, but can we see how that arises? Unless, because here what's easy, here there is G mu nu and sort of, you know what you need to identify. But if you have another theory, if you have, well, say n equals 4 super Young Mills, then how would you see the emergence of the equations from, or maybe just a two-dimensional CFT? Right?
Yeah, so I think the best answer I can give is, well, I think the way I would proceed is to try to understand, the kind of questions that I asked about just trying to very directly connect this to a gravity action, period. And then maybe understand this nonlinearity a little bit better, because just starting from JT gravity and trying to generalize a little bit more, we can think about adding a potential for the dilaton. So then Einstein's equations become nonlinear in the dilaton, and also if you had a potential for the dilaton, the metric here wouldn't be rigid; it would be fluctuating. And so what happens, I think, is that you both have a fluctuating probability measure for the quantum observable. So in the JT case, we had just a rigid measure for the probability of rigid measure on ADS2, which corresponds to the fact that we have sort of this exact measure for the observable. So this would be fluctuating if you add a potential, plus the Einstein's equations would be nonlinear. So we have to understand both of what's going on in that case. So I mentioned this a little bit about how there's this generalization of Markov processes to nonlinear Markov processes. So yeah, if you look back to the discussion of Markov processes, so in this kind of language, you can only get a linear equation because you have, so where did I have the, yeah, so in this kind of language, you have a distribution and then you have some kernel acting on the distribution. So the equation is linear. So we have an expression that's linear in the distribution, and the idea of a nonlinear Markov process is that not only would the distribution at a later time depend on the initial, how to say this? Yeah, so the idea of a nonlinear Markov process would be that this probability kernel itself depends on the probability distribution as well. So instead of having some probability kernel that doesn't depend on nu, it does depend on nu. So you can get nonlinear equations. So that way you can sort of try to imagine how that could correspond to Einstein's equations in the presence of a potential for the dilaton. And then, but the thing is that you would also have a fluctuating background measure. which is sort of an exact quantum measure for this observable. So yeah, there are many pieces that I'd like to think about. And I think, yeah, answering those questions, that we might start to get a better picture of, how can we talk about more complicated systems like n=4 super Young meals and so on.
Can I ask you a very difficult and unfair question, which is, what's the timescale for this paper to come out? I mean, if you ask me, for me, it's always 2 weeks in the future, and then a year later, it's still 2 weeks in the future. But
oh yeah, yes. So really, I am aiming for the end of February. Yeah.
End of February. Okay. All right.
Thank you. Other questions?
Yeah, I had a quick one. Thanks for the nice talk, Josephine. So I was curious about your results and how they relate to this other paper by Stanford and Yang, who give the regularization of the JT path integral in terms of self-avoiding loops. And as far as I could tell, that self-avoiding constraint is something that survives the flat space limit. So I was kind of curious, does your analysis go through, or does it depend on specifically this regularization in terms of world line of a particle?
Yeah. So self-avoiding loops, I think that refers to a limit of parameters such that the particle doesn't intersect itself. And that's actually the same limit that we work. That's always the limit that you work with actually when you talk about there being a gravity dual, because it turns out that that limit is kind of it's basically the large N and strong coupling limit, in which we usually think about there being a classical gravity dual to the quantum theory. So what I said is actually, when I said I have to take some limit in order to have this Markov process, that limit of parameters was I had to take that limit also in this analysis. So yeah, it's basically the limit of large N and large coupling in the microscopic language. In this particle language, it's the limit of large spin and low temperatures. And on top of that, I also took the semi-classical limit, meaning N very large compared to beta J, to inverse temperature. Yeah. So in addition to this limit of what is it called, non-intersecting loops, I also take this semi-classical limit.
Okay, yeah, I was a bit confused because I think they don't make any. I don't think there's reliance on deriving it from SYK. I think they just start from JT gravity or something like this. So is it? So there's some parameters, some limit that you're taking within just JT itself?
Yeah, exactly. So I said large N and low temperature. Here it's large spin. So large spin corresponds to large N and also low temperature. There is a temperature in here. It's the temperature of the thermal density matrix of the particle.
Okay, and do you have any thoughts about maybe where those differences could show up, or if those would be interesting at all?
What differences?
Well, just dependence on sort of like, do you not expect that to be important for the derivation of Einstein's equations or something like, just the fact that there's a different regularization that has some non-local, that's not just a free particle moving in a background, ADS background.
Yeah, so I'm actually not super familiar with what the different regularization that you're talking about is. What is the different regularization?
Well, it's so we can talk about this another time, I suppose, if it's too much. But it's in terms of basically instead of describing it's also including constraints that, because here the particle is describing the boundary of your ADS space. And one should also impose the fact that the boundary never self-intersects.
Okay.
And so I guess for some questions, that's an important assumption to include, but it's not always important, as you said, depending on the limit.
Yeah, because if you take a limit, if you take certain parameters in the theory to be large, then that constraint sort of happens dynamically. So dynamically, it just happens that the particle doesn't want to intersect itself if you take the spin to be large and the temperatures to be low. So I suppose you could also think of, directly imposing that constraint just exactly. And yeah, maybe you could.
Well, I guess could you clarify how you're both taking the, maybe these are separate, maybe these are separate parameters, but both low temperature, but also short time limit on a propagator?
Yeah, so basically we have two parameters in the theory. So the spin and also the temperature appearing in the density matrix of the particle. And so, as I said, we take the inverse temperature and the spin to be large. And then, so those are the parameters, but actually in these quantities, we also have this short time. We have this proper time appearing in the propagators, right? And so we compute the exact propagator for the particle, starting from the world line action. And then we can take an asymptotic limit. Well, okay, I have to be careful. So I starting with an exact expression for the propagator, we take the limit that we discussed of large spin and low temperature. And then as an additional step on top of that, we have to look at the limit that these proper times are very small. So what happens is that you have a differential equation that solves for these propagators. And there's a specific way of going to this asymptotic limit. It's actually easiest if you start from the differential equations. And that approximation only applies when this time is small.
Can you remind what spin correspond to in JT action?
Yeah, so the spin is actually the value of the dilaton at the boundary. So the spin term originated from this boundary curvature term. So it's related to the value of the dilaton at the boundary, which we actually fix. So it's the boundary condition when we solve the gravity problem is that we fix the value of the dilaton at the boundary.
Thanks.
So I made Sergey host because I have to leave for another Zoom meeting. So thank you, and please continue the discussion as long as necessary. It will be up to Sergey to stop the recording at this point. Okay. So thank you very much, and please continue as long as you want.
Thank you.
Actually, I also have to go to pick up my son very soon. But yeah, I'm not sure. Are there any more questions? No, it looks like that's it. Thanks a lot for the very nice talk.
Thank you so much for having me. Yeah.
Thank you, Josephine. That was a great talk. Thank you.
Yeah.